Hey, I have a question. Why do SpaceX and NASA build rockets that look and work so differently? After all, they're both trying to get things into space. Well, then that's what we're going to find out. Today, we'll compare some of the biggest rockets from SpaceX and NASA, looking at their capabilities, costs, engineering choices, and overall design philosophies. We'll see why two organizations building rockets can arrive at such dramatically different solutions, and why both approaches make sense for the missions they're trying to accomplish. And of course, we'll tackle the ultimate question. In this new era of spaceflight, which design philosophy comes out on top? Let's get into it. Okay, first, let's make this easier to visualize by bringing out a few of NASA's and SpaceX's rockets for comparison. And to make things interesting, we're not starting small. We're going straight for the big guns. In this case, that means the giant super heavy lift rockets. These are the monsters of the rocket world. They can launch massive payloads into orbit, carry large spacecraft toward the moon, and even send probes directly to the outer solar system without needing years of gravity-assist flybys from planets along the way. For NASA, that rocket is the Space Launch System, better known as SLS. For SpaceX, it's the rocket that has probably generated more headlines than any other in recent years, Starship. Let's start with SLS, the rocket currently responsible for carrying NASA's Artemis missions toward the moon. Development began in 2011, and after more than a decade of work, it finally made its first flight on Artemis 1 in 2022. Standing nearly 98 meters tall and weighing around 2,600 metric tons at liftoff, SLS is one of the largest and most powerful rockets ever built. In other words, if rockets were pickup trucks, SLS is the giant heavy-duty model designed to haul a house across the country while towing a boat just because it can. But here's the thing. SLS is less a brand new rocket and more a carefully assembled collection of Space Shuttle hardware. Its core stage, built by Boeing, is powered by four RS-25 engines originally developed for the shuttle program. These engines burn liquid hydrogen and liquid oxygen, producing incredible efficiency. In fact, the RS-25 remains one of the most efficient large rocket engines ever built. To get the rocket off the pad, NASA adds two giant 5-segment solid rocket boosters built by Northrop Grumman. Together, the engines and boosters generate about 39 meganewtons of thrust at liftoff. That's a lot of power. Roughly enough to lift several aircraft carriers if physics worked the way cartoon logic thinks it does. SLS can carry around 95 tons to low Earth orbit and roughly 27 tons toward the moon in its current Block 1 configuration. Future versions could push over 40 tons toward lunar destinations. The catch is that all of this is insanely expensive. Depending on how the accounting is done, a single SLS launch currently costs somewhere around $2 billion or more. That's not a typo. Every launch costs about as much as a blockbuster movie franchise. And because SLS follows the traditional rocket design philosophy, almost everything is thrown away after launch. Once the mission is underway, that's it. The rocket's job is done. The core stage is gone, the engines are gone, the solid rocket boosters are gone. Some parts fall back into the ocean, while others burn up in the atmosphere during re-entry. Either way, none of it is recovered and reused. Which brings us to Starship. If SLS feels like a handcrafted luxury watch, Starship feels like SpaceX looked at the entire rocket industry and asked, what if we did the opposite, literally? Starship currently stands around 121 to 124 meters tall, making it the tallest rocket ever built. Fully fueled, the stack weighs roughly 5,000 tons, nearly double the mass of SLS. Then there's the thrust. The Super Heavy booster uses 33 Raptor engines, generating somewhere between 74 and over 90 meganewtons of thrust, depending on the configuration. That's more than double SLS and nearly 3 times what was available on the Space Shuttle. The engines themselves are fascinating. While SLS relies on liquid hydrogen, Starship uses methane and liquid oxygen. Methane is slightly less efficient than hydrogen in a vacuum, but it's denser, easier to store, cheaper to handle, and can theoretically be produced on Mars. Because apparently, SpaceX looked at launching rockets and immediately started planning for gas stations on another planet. Starship's biggest innovation isn't raw power, though. It's reusability. The Super Heavy booster is designed to fly back to the launch site and be caught by giant mechanical arms. The upper stage is designed to survive re-entry, land, and fly again. Instead of throwing away a rocket after every launch, SpaceX wants to operate rockets more like commercial airplanes. That's why Starship's target launch costs are measured in the tens of millions of dollars rather than billions. The entire economic argument is simple. If you stop throwing away the vehicle, spaceflight becomes dramatically cheaper. To drive costs down even further, SpaceX decided to build the world's largest rocket out of stainless steel. When they first announced that idea, a lot of people thought they'd completely lost it. After all, rockets are supposed to be made from exotic, lightweight aerospace materials, not the same stuff you might find in a kitchen sink. But as it turns out, there was a method to the madness. Yes, stainless steel is heavier than advanced aerospace composites and aluminum alloys, but it's also dramatically cheaper, easier to work with, incredibly durable, performs well at the super cold temperatures of liquid methane and liquid oxygen, and can handle the intense heat of re-entry surprisingly well. Most importantly, it lets SpaceX build rockets fast, really fast. Engineers can weld together new designs, test them, watch them fail spectacularly, make changes, and build the next version in a fraction of the time traditional aerospace programs typically require. At times, it feels less like a rocket company and more like a software startup that somehow got access to giant rocket engines. SLS takes almost the exact opposite approach. Its massive core stage is built from advanced aluminum-lithium alloys and covered in the familiar orange foam insulation inherited from the Space Shuttle era. These materials help keep the rocket as light and efficient as possible, squeezing every bit of performance from the vehicle. The trade-off is that they're far more complex and expensive to manufacture. Building SLS requires specialized facilities, highly trained workforces, strict quality control procedures, and production timelines that are measured in years rather than months. It's a more traditional aerospace philosophy: move carefully, verify everything, and prioritize reliability over rapid iteration. Of course, it's still far too early to declare Starship the winner. Right now, Starship is still very much a vehicle in development. The rocket has demonstrated incredible progress, but some of the hardest parts of the program are still ahead.
Its heat shield, orbital refueling system, and rapid turnaround capabilities are all works in progress. The architecture looks revolutionary on paper, but SpaceX still has engineering hurdles to clear before the vision becomes reality. Now, it wouldn't be fair to NASA if we're bringing SpaceX's biggest and most ambitious rocket to the table and do not mention the grandfather. The legend, the rocket that actually took humans to the moon. Because for all the excitement around Starship and SLS, Saturn V remains the benchmark every heavy-lift rocket gets compared against. Built in the 1960s for Apollo, Saturn V stood about 111 meters tall, weighed nearly 3,000 tons, and generated around 35 meganewtons of thrust at liftoff. Unlike Starship's methane engines or SLS's shuttle-derived RS-25s, Saturn V used 5 enormous F1 engines, burning RP-1 kerosene and liquid oxygen. Each F1 engine produced about 1.5 million pounds of thrust by itself. Even today, more than half a century later, the F1 remains one of the most powerful single-chamber rocket engines ever flown. Saturn V could place roughly 140 tons into low Earth orbit and around 45 tons on a direct trajectory to the moon. That's actually one area where Saturn V still impresses. Despite being designed with slide rules, paper calculations, and computers weaker than a modern smartwatch, it remains extremely competitive with modern heavy-lift rockets when it comes to sending payloads toward the moon. Saturn V achieved this through brute force. No reusability, no orbital refueling, no fancy recovery systems. Launch it once and throw everything away. Saturn V represented a time when the goal was simple: beat the Soviets to the moon, no matter the cost. At this point, you're probably starting to notice a pattern. Almost everything SpaceX does ultimately serves one giant objective: to make rockets reusable and fly them again with as little refurbishment as possible. That's not just a feature of Falcon 9 or Starship, it's the entire philosophy. The restartable engines, the precision guidance systems, the throttleable rocket engines, the hypersonic grid fins, the autonomous landing software, and even those giant chopstick arms at Starbase all exist for one reason: bringing hardware home instead of throwing it away. If the booster can return directly to the launch site, great. If it can't, SpaceX parks an autonomous drone ship in the middle of the ocean and lands on that instead. Because apparently recovering a rocket from a moving platform hundreds of kilometers offshore is now considered routine. And reusability isn't the only thing SpaceX obsesses over. There's also speed. Traditional aerospace development often moves at a pace that can best be described as carefully scheduled paperwork. Major design decisions can take months, sometimes years, to work their way through reviews, approvals, and endless meetings. SpaceX looked at that process and essentially said, what if we just built the thing and found out? The company follows a build, fly, learn philosophy. Prototypes aren't treated as priceless museum pieces. They're treated as experiments. Build one, launch it, see what breaks, fix the problem, and build the next version. Sometimes that process produces spectacular successes. Sometimes it produces what SpaceX politely calls a rapid, unscheduled disassembly. Either way, they get data. This rapid iteration is possible because SpaceX operates with an unusually high degree of vertical integration. At its facilities, engineers, manufacturing teams, and test operations are often working side by side. Decisions that might take months elsewhere can sometimes happen in days or even hours. The goal isn't perfection on the first try. The goal is to learn faster than everyone else. NASA, on the other hand, approaches the problem from almost the opposite direction. For NASA, the primary question isn't how fast can we improve this, it's how do we make sure this works when astronauts are depending on it. Space is an extraordinarily hostile environment. Radiation can damage electronics and weaken materials. Temperatures can swing from blistering heat in direct sunlight to extreme cold in shadow. Vibrations during launch can shake components apart. Micrometeoroids don't care about your project schedule.
Because of this, NASA spends enormous amounts of time selecting materials, testing components, validating designs, and analyzing potential failure modes long before a rocket ever reaches the launch pad. Every material must justify its existence. Every component must prove it can survive the mission. Every system is tested, reviewed, and tested again. This often means using expensive materials, extensive qualification programs, and years of verification before all the pieces are finally assembled into a flight vehicle. It's a slower process, but one designed to maximize confidence and minimize surprises. And that's really the fundamental difference between the two organizations. SpaceX is willing to accept more risk during development in exchange for learning quickly and driving down costs. NASA is willing to accept slower development and higher costs in exchange for greater confidence, reliability, and mission assurance. Neither approach is inherently right or wrong. They're simply optimized for different goals. SpaceX wants rockets that can fly again tomorrow. NASA wants rockets that absolutely work when the mission of a lifetime is on the line. And when you compare their materials, manufacturing methods, and development cultures, those priorities become impossible to miss. No matter which approach you prefer, it's hard to deny that SpaceX has already changed the aerospace industry. A decade ago, the idea of building, testing, and flying major rocket hardware at the pace SpaceX does today would have sounded completely ridiculous. The traditional model was slower, more cautious, and often measured progress in years. Now, even long-established aerospace companies are trying to adopt faster development cycles, more iterative testing, and some version of the agile engineering philosophy that SpaceX helped popularize. The problem is that changing a culture can be harder than designing a rocket. Many traditional contractors were built around decades of processes, reviews, and organizational structures that prioritize predictability over speed. Those systems exist for good reasons, but they can also make rapid innovation feel a bit like trying to turn an aircraft carrier with a canoe paddle. That's one of SpaceX's biggest advantages. They didn't have to reinvent an old culture. They built a new one from scratch. And that advantage may become even more important as the industry enters its next phase. Looking ahead, the next major breakthroughs could come from things like AI-assisted engineering, automated design optimization, and eventually even manufacturing hardware directly in space. Those ideas may sound futuristic today, but so did landing orbital-class rocket boosters a decade ago. In many ways, Starship is becoming a giant testbed for the future of spaceflight. Beyond simply carrying cargo and crews, it's giving SpaceX a platform to experiment with technologies that could define the next generation of spacecraft. Meanwhile, reusable rockets are rapidly going from a crazy idea to the new industry standard. More companies are chasing that goal every year, but for now, SpaceX still has the advantage of being the company that got there first, and keeps pushing the technology forward at a pace that's often difficult for competitors to match.
So, does NASA still have a role in this new future? Absolutely. In fact, you could argue that NASA should keep doing what NASA has always done best. Because, despite what internet comment sections sometimes suggest, building rockets has never been NASA's only job, or even its primary purpose. NASA is not a commercial launch company. NASA's job is to explore, conduct research, develop new technologies, manage ambitious missions, and push the boundaries of what humanity knows how to do. Or, put another way, NASA's job isn't necessarily to build every truck. It's to figure out where the road should go next. That's a distinction people often miss. Yes, NASA engineers have historically done enormous amounts of design work, testing, systems engineering, mission planning, and technology development. But even during the Apollo era, NASA relied heavily on contractors to manufacture the hardware. Take Saturn V. People often talk about it as if NASA built the rocket directly. In reality, major portions were manufactured by companies like Boeing, North American Aviation, Douglas Aircraft, and others. NASA defined the requirements. NASA designed the missions. NASA developed much of the technology. NASA tested and integrated the system. But the industry built much of the hardware. That's been the model for decades. And it's one reason NASA plays such a critical role in today's space industry. NASA creates demand. Think about it. NASA paid SpaceX to develop cargo transportation to the International Space Station. NASA later funded crew transportation capability. Today, NASA is paying SpaceX to develop a lunar version of Starship for Artemis. Without those contracts, many of these programs would have been significantly harder and slower to finance. In many ways, NASA acts as the customer willing to invest in technologies that don't yet have an obvious commercial market. And that's something private companies often struggle to do on their own. The same thing is true for reusable rockets. You'll sometimes hear people say, NASA invented reusable rockets decades ago. That's both true and not quite the whole story. The idea of reusable launch vehicles existed long before SpaceX. NASA, the Air Force, and numerous aerospace companies studied reusable rocket concepts throughout the 1960s, 70s, 80s, and 90s. Projects like the DCX demonstrated vertical takeoff and vertical landing technology years before Falcon 9 ever existed. The challenge was never proving that reusable rockets were theoretically possible. The challenge was making them practical, making them reliable, making them rapidly reusable, making them commercially competitive, and perhaps most importantly, making them profitable. That's where SpaceX deserves enormous credit. It's a little like aviation. The Wright brothers didn't invent the dream of flight. People had been dreaming about flying for centuries. They were the ones who actually made controlled, powered flight work. Similarly, many organizations helped prove reusable rockets could work in principle. SpaceX proved they could work as a business. Another thing worth understanding is that NASA and SpaceX operate under very different incentives. Historically, NASA programs have been deliberately spread across multiple states. You've got Johnson Space Center in Texas, Kennedy Space Center in Florida, Marshall Space Flight Center in Alabama, Jet Propulsion Laboratory in California. Major contracts are often distributed across many companies and congressional districts as well. This approach creates jobs, political support, and national investment across the country. Critics sometimes call this the political geography of NASA spending. NASA pushes the frontier. SpaceX helps make access to that frontier cheaper. NASA explores planets. SpaceX builds the transportation. NASA develops new technologies and funds research. SpaceX turns those breakthroughs into practical systems. One helps humanity figure out where to go next. The other is working on how to get us there more often, more cheaply, and eventually in much larger numbers. And if humanity ever does establish permanent settlements on the Moon or Mars, chances are we'll look back and realize it took both organizations, working in very different ways, to make it happen.